Welcome back. So we'll take one last example on the use of position vectors. Of course, we will continue to make reference to position vector concepts as we proceed with this course. Okay, this is just the last example for this chapter, not the last time you are going to need to make use of position vector concepts. Okay, so now let's look at these. It says, okay, worked examples. Right. So this problem says prove that prove that the medians of a triangle, the medians of a triangle are concurrent. Prove that the medians of a triangle are concurrent. Firstly, what do we mean by concurrence or concurrency or concurrence, if you like? This is implying that they meet at a point, okay, or emanate from the same point. So if we say medians of a triangle, we've talked about that already. The line drawn from one vertex of the triangle to the midpoint of the opposite side. Okay, so that is what we mean by median of a triangle. So for medians of a triangle, that means we refer to the three medians we can have for the triangle. So we want to show that those three medians actually meet at a point. Okay, that is what we mean by concurrent. That is, they all intersect, the three medians intersect at a point, at the same point. Okay, so how do we go about this? Here again, we will make use of position vector concepts, and the results we also have obtained in the last chapter when we talked about the median of a triangle. So I hope you still remember that result. It's some of those things you should know already, and you should be able to easily recall at every point as we proceed with this course. You will need the results at different points, so it's good that you have them um, already retained somewhere in your mind. Okay, so now let's move on. We have a triangle. In this case, we are not given any letter for representing the triangle, so we're just going to pick arbitrary points to represent the vertices of the triangle and also the midpoint of the sides. So let's say that we have an arbitrary triangle. Okay, just any kind of triangle now. It doesn't have to be a special triangle. So we have these points as one vertex, this as another vertex, this as another vertex. So let's say that this is point A and this. So let's say this is point A and this is point B and this is point C. So if that is the case, I mean, this is our choice now. We just choose that. Then we're interested in the medians of the triangle. So for the medians, as we did before, the side opposite A, its own midpoint is going to be somewhere around here. So let's call that D. So I've taken A, B, C. So let's call this D. And then the side opposite B, okay, its own midpoint. Let's say that midpoint is here. Let's call that E. And then the side opposite C, well, we locate its own midpoint and let's call that DEF. Okay, so this is the F. Okay, so we can now draw the medians. Median simply means the line that goes from this midpoint to the vertex here. So this is the median for this side. And then we draw for the points E, from point E to B, for instance, that goes from this point to this point. Okay, so we know that definitely if we draw two lines, those two lines passing this way will intersect. Okay, so this is their point of intersection. Okay, let's call this point of intersection point Q or point whatever you want to call it now. So let's say this is point of intersection. We are calling it point Q. So what we want to establish is that the three lines, these three medians are concurrent. So if they are concurrent, that means if we were to draw this third one as well, it will pass through this same point of intersection of these first two will be the same point that the third one passes through. So to prove that the medians are concurrent is to establish or prove that having chosen any two of them and taking their point of intersection, we also want to prove that the third one will pass through the same points. So that is the idea. So that's what we want to do here. Okay. So we say that given that or knowing that Q is the point of intersection of the medians through points E and F of the medians through points E and F, we need to show that the median through D, the median, we need to show that the median through point D, okay, passes through the same points, okay, that is, it touches the same point. Q passes through the point Q or intersects the point Q, okay. So that is the idea. What have we done here? We have taken the problem statement and interpreted it in the context of this diagram we have so far drawn. So we have drawn this diagram. We're saying that let Q be this point, okay, that the median here and the median here intersect. We know they are definitely going to intersect. Okay, so that's not what we're trying to drive at. What we're driving at is that all of these medians, so including the third one, will also pass through the same point. That means the third one will pass through the same point of intersection of these first two. So we have chosen an arbitrary point Q as the point of intersection of these two, because the fact that these two will intersect is not in doubt. Okay, they are passing through this point, they will definitely intersect. Okay, so the idea is that, of course, if this is going to pass through here, it might pass through it in such other way that it is not passing through these midpoints. Okay, it's possibly passing this way, but we want to show that it actually does. And so far this is a midpoint, as this is a midpoint and also this is a midpoint, then definitely this is going to pass through this point. That's what we want to show now. Okay, so now we have chosen the point Q as the midpoint. Now we need to write out the mathematical implications of this being the midpoint of this side of these 2 points, and this being the midpoint of this side, also this being the midpoint of this side, because those are the things we will make reference to actually establish this relationship we need to establish. That is, we need to go from what we know about this geometry to establishing what we need to know. Okay, so we know for this geometry that E is the midpoint of A and C. So if we pick an arbitrary point O, that point O can be just anywhere now. So let's say this is point O. We can use it to, take the position vector for each of these points. So we can say that there's a position vector for A, there's a position vector for E, there's going to be a position vector for C as well. Okay, so we'll come back to that shortly. But if we look at the point O now, so think about what happens, or what is the relation between points O, E, and AC. So look at that. We say that this goes through this point and it touches to this, and that is vector OE. So if we look at that from what we did in the last chapter, you should remember that for the median, so looking at this now, This is a triangle on its own. This OAC is a triangle on its own. And this line from O to E is a median of the triangle OAC. So if you're able to detect that easily, then you can write that since E is the midpoint of side AC, since point E is the midpoint of side AC, then what can we say from that? It will follow that from what we've done before, we should have it that OE will be equal to half of OC plus OA. Okay, you should remember that we dealt with something like that in the last lesson. That if you have, let's quickly draw that out here. I'm going to wipe it off shortly. That if you have this as the midpoint of this, okay, so let's say this is A, B, C, and this is midpoint, which is D. We're able to establish that this line AD was going to be equal to 1 over 2 of AC plus AB. So that is AC plus AB. So basically, that is the same idea we use here. And of course, I told you then that you can easily memorize this, so to speak, or easily recall this relation by going with the fact that this is the midpoint of B and C. That is, this is the middle of B and C. So by the time you add the coordinates of B and C together, and divide them by and divide the result by 2 to give you the coordinates of the point D. So definitely that is the way to relate with this equation. Okay, and so exactly the same thing is playing out here. E is the midpoint of A and C. So if I add the coordinates of C and A together, so and I divide by 2, it will give me the coordinate of point E. So just in the same manner as this is a triangle, just like we have this to be a triangle. So you can imagine that you have O to be OAC to be a triangle. So this is a median of the triangle. So we can write the same relation that OE will be equal to OA plus OC. Okay, and so we can just put that out directly here to say that we have OE will be equal to OA plus OC then divided by 2. So it will be 1 over 2 of all of this. Okay, so that's basically what we've done here. OE will be equal to half of OC plus OA. And of course, we now know that a better representation for this will be that OE is the position vector of point E relative to point O. OA is position vector of point A relative to point O, and OC is position vector of point C relative to point A. So if we will deal with that, then we can say that let the point E now represent this OE. Now we can say E will be equal to 1 over 2 into A plus C. Okay, since we have the same reference for all of them. Okay, so this will be 1 over 2 into A plus C. So let's keep that as one of the things that may help us along the way. Okay, or that will become useful along the way. Right, so that is for this side. And this is just due to the fact that E is the midpoint of of A and C. So E is the midpoint of A and C. So position vector represents point A plus the position vector representing point B. When we divide by 2, it will give us the position vector representing point E. So that's exactly what we have here. So similarly, we will have the same results if we consider this side, since D is the midpoint of B and C. Then the position vector representing B added to the position vector representing C and divided by 2 must give us the position vector representing D. Okay, so we now say that similarly, so we don't have to go through all of these processes any longer. We can say that similarly, since we have, where's that point again? D is the midpoint of B and C. Okay, so we can write that D, that will be vector D representing position vector for D, will be equal to 1 over 2 into B plus C. Okay, so we can keep that as well and say that is equation, say equation 2. And then we move to the next one. F is the midpoint of A and B. So if we use small f to represent the position vector for the point F, then it will follow that F will be equal to 1 over 2 of A plus B. All right, and then we can say that that is equation 3. So let's keep these tools for now. Okay, so we'll come back to that. Now the next thing is this. What is the implication of this statement or this observation? If this, okay, if this median from E to B or B to E if you like, and the median from C to F meets at this point or intersect at this point, as we have said, that is the meaning of the point Q, then what is the implication of that mathematically? You know, there are three facts now that we have established, and we have written out their mathematical implications. Okay, one of them is that E is the midpoint of AC, so we have written out its mathematical implication. D is midpoint of BC, we have written out its mathematical implication. F is the midpoint of AB, we have written out its mathematical implication as well. So the next thing is that Q is the point of intersection of FC or CF and BE. So what is the mathematical implication of that? We need to write it out as well before we can proceed with any other thing. Okay, so pay attention now. How do we do that? So looking at this, CF. So if you imagine the vector CF, then vector CF will be along the same line as this vector CQ. Again, let me repeat that. Vector CF is clearly along the same line as vector CQ. Okay, that is, you can say that it is parallel to it, you can say it is collinear. Okay, we've discussed that already in the last chapter. It is collinear means that they're both along the same line. Yes, that is how this makes sense. So the vector CF, if you like, and the vector CQ are on the same line. That means vector CQ and vector CF are collinear. And similarly, vector BQ and vector BE are collinear. So those are the things we can deduce from this. So what's actually what part of the statement actually like um, hits the nail on the fact that these two intersect. The fact that both equations involve Q means that they both intersect at the point Q. So that is the idea. All right. So that means that both vector or line vector CM and line vector BE intersect at the point Q. Okay. Since we're able to establish that relation and we're able to carry it through, relate it with a vector that goes from C to Q and then from Q to F. And then we do something similar here and relate that to the vector that goes from B to Q and then Q to E. Then we have been able to establish that indeed, or we have been able to hit the nail on the fact that they actually intersect at the point Q. Okay, so we need to write out those mathematical implications now. Okay, and don't forget what is the implication of collinearity. If two vectors are collinear, we've talked about that already. It means that we will be able to write one of them as a multiple of the other. Okay, so we now say that. So let's have an additional page first. So we now say, furthermore, since medians, where are those medians now that we've just drawn? CF and BE. We just pick any two of them. You know, you could have started out with what's that now? AD and let's say BE. It's fine. That means you want to prove that the third one passes through that point, okay, from the result. Okay, so we're just starting out with any two. Then from whatever we're able to get from those two, we want to establish that the third one also passes through that point. Okay, so that's what we want to do. And so proceed now, since the median CF and BE, okay, intersect at the point Q. They both pass through the point Q. Then, since medians CF and what's that now? BE pass through and also intersect, of course, the point Q. Then we say that the vector CQ, so you can take them anyhow you like, just be consistent with the relation so that you can get a consistent set of equations to deal with. So we can say that the vector CQ is collinear to the vector CF. So that means that vector CQ and CF will be on the same line, all right? You know that if it was not along this line, if they did not intercept, now think about it, if they did not intercept, if this was not along this line, or if Q did not lie along the line, we could have something like, let's say this is point F and this is point C, and then this is the line joining the two, and then point Q is not on the line. Let's say point Q is here. If point Q is here, we can still define the vector CQ and vector CF, but then it will not be on this line. So vector CQ, in this case now, vector CQ is collinear, is on the same line as vector CF. But if this Q was not on this line, then we would not be able to make that statement. And so the vector implication of collinearity will not apply if Q was not on this line. Okay, so that's the idea. So we have taken that into consideration already. When we say that these two are collinear, that means we are already recognizing that Q lies on the line from C to F. Okay, so we now say that CQ is collinear, CQ and CF are collinear. So that is one statement. I will say that then CQ and CF CQ and CF are collinear. Okay, that is one. Also, we know that for the same reason, I mean, this is for when we consider the line CF or the line vector CF, if you like. If we consider the line vector, if we consider the line vector BE, then that means BQ and BE are collinear. Okay, just like we have CQ and CF here. So, and also BQ and BF, okay, are collinear. Sorry, not BF now, BE. BQ and BE are collinear. So we just know that they are collinear, they lie on the same line. We don't know how far B is from Q relative to how far it is from E. We don't know how far C is from Q relative to how far it is from F. Okay, but we just know they are collinear, all right? And now we should remember that for collinear vectors, it simply means that we can write one of them as a multiple of the other, okay? Because the only difference will be in their length, okay? They will have the same direction. So because of that, we can write one as a multiple of the other. So because of these statements up there, we can now write that therefore CQ can be written as a multiple of CF. Okay, so we can write CQ as a multiple of CF. Of course, we might expect that okay, CF is longer, obviously. CF is longer, so it should be the one we write as a multiple of CQ. That is fine as well. But the point is that it's a multiple. Multiple does not mean it has to be greater than one. Multiple can be less than one. Okay, so I can say that we can find out now, for instance, that CF, I'm not saying that's the case, but I say we can find out that CF is 0.5 CQ. So if we write CF as multiple of CQ, that is fine as well. We just find out that the actual number is something less than 1 because CQ is actually less than CF. We can also write CQ We can also write CF as being a multiple of CQ. In that case, we'll have a number that is greater than 1. Okay, so if we write CQ as multiple of CF, we have a number that is less than 1. If we write together, we have a number that is greater than 1. It doesn't matter. What's important is consistency. So if we are taking CQ as a multiple of CF, then we should also take, for consistency now, BQ as a multiple of BE. So once that consistency is there, then there is little or no room for confusion. So let us go ahead and just say that CQ is a multiple of CF. So CQ is a multiple. Multiple of simply means when we use some real number to multiply CF, it will give us CQ. So we don't know what that real number is, but we can use lambda, okay, like we have always used. All right, so we can say this should be equal to lambda CF. So if they are collinear, then I can write one of them as a multiple of the other. All right. So we'll come back to the implication of this. All right. So for now, let us keep it. Okay. As okay, let's simplify it further. Should we simplify it further? Yes, we can simplify it further as it is. So we have CQ. Just as we have our equations here in terms of position vectors, let us also simplify this so that it is in terms of position vectors. And if we will do that, it will follow that we'll have this to be CQ. CQ will be Q minus C. That's position vector of Q minus position vector of C. So this will be equal to Q minus C. All right. Then this will be equal to lambda into C. Okay, CF. That will be F minus C. So we have this relation. If we will make Q the subject here, for instance, you see shortly while we are doing that, if we make Q the subject, I mean, this is just a bracket, there's nothing multiplying it outside, so we can just ignore the bracket, then we'll move C to the other side. Then we're going to have this to be lambda. If we open up this bracket, this is lambda F minus lambda C. Okay, so before we do that, we can say that this is Q minus C equal to lambda into. So this is the idea now. You see why we're doing this shortly as we proceed. Now we want to write this relation first. We want to find an expression for Q in terms of the position vectors of points A, B, C, which are directly related to the triangle, the vertices of the triangle. Okay, so we want to write the position of Q in terms of those of A, B, C. That is our objective for now. We'll come back to make use of that in establishing that indeed this line AD will pass through the point Q. So how do we go about that? We have an expression for that here already, so we just need to simplify further. What do we do here? The only thing that is not of ABC here is the point F or the vector F, which is position vector of the point F. So how can we get rid of that? That is quite easy because we already have an expression for F in terms of A and B, which apply to the vertices of the triangle, right? So we can just make the substitution here, all right? So we can say that instead of this F, you can have this to be, so let's use a bigger bracket here. So instead of F, we can write this to be 1 over 2 into, so what do we have there? This says, equation 3 says 1 over 2 into A plus B. So we can write this as 1 over 2 into A plus B. Okay? Then minus C. So that's what we have right here, F minus C. So with this, we are good to go. We have a relation between Q, A, B, and C. So that is the relation between the points of intersection that we're interested in and the position vectors of the vertices of the triangle. So it's easier to relate this with the position vectors of the vertices of the triangle this way. So by simplifying for that, this will give us Q equal to, I'll move this to the other side. So let's open up this bracket first. This is going to be lambda over 2, lambda times this, lambda over 2 multiplying A, then lambda over 2 times B, that will be plus lambda over 2 multiplying b. Then we have lambda multiplying c. Okay, that was minus lambda multiplying c. Okay, so this is minus lambda multiplying c. Then we move this minus c to the other side. That becomes plus c. So we can simplify this even further and say that what we have here, of course, don't forget that how we came about this is by using equation 3 up there. So this is from equation 3 up there. So when you come across it, you know exactly what we did. We removed f and replaced it with 1 over 2 into a plus b from equation 3. So that's how we came about this. We just removed this f and replaced it with this. Okay, and from here, we can simplify this even further to say that Q equals lambda over 2a plus lambda over 2b. Then for C, if we factor out C here, this will be plus 1 minus lambda multiplying c. Okay, so that is the relation between q and the position vectors of a, b, and c. But we don't know what lambda is. Okay, so we'll come back to deal with that. We don't know what it is for now. Let's leave it at that. So let's say this is equation 4. Then to proceed, we came about this by considering the fact that by considering CQ and CF being collinear. So now let us consider BQ and BE being collinear. All right. So similarly, for BQ and BE, for BQ and BE, for the collinearity of BQ and BE, what do we do now? We say that BQ, just like we wrote it here, CQ is lambda CF. But we don't, or we cannot use lambda now because we are not sure. There is no information supplied here that tells us that it is as far from this point to this point as this is from this point to this point. So we don't know that ratio yet. We're not sure of it. So we don't know how big B, where is it now? We don't know how big BQ is relative to QE. Okay, so we cannot use lambda like we used up here. All right, so we just use something else. So we now say that in this case again, BQ be equal to, let's say we're using alpha now. So this will be alpha of B. Okay, just like here we used lambda to communicate to that collinearity. So we're using alpha here. So again, we follow the same approach and simplify this and see what it gives us in terms of Q. So going further, by our position vector approach, we know that BQ will be Q, position vector of Q minus position vector of B, that's Q minus B, and this will be equal to alpha into BE. That will be E minus B. And what do we have here again? We have E, which is not one of the vertices or position vector of one of the vertices of the triangle. And so, like we did for F here, it is good that we get rid of E as well. So if we will get rid of E, what are we going to use? So we just come here and locate E. In equation 1, we have E already to be equal to 1 over 2 of A plus C. So we're going to use that right here to simplify this. So we now go ahead to say that this implies that Q minus B is equal to alpha into, instead of E now, we use 1 over 2 into A plus B. That's correct. Is it A plus B right there? Please let us be sure. E is actually 1 over 2 into A plus C, please. A plus C, not A plus B. Okay, so let us correct that. It is A plus C. Right. Then minus B. Okay, so with this now, we have only Q and the coordinates, or say the position vector of the vertices of the triangle. So with this, we are good to go just like we were right here. So let's simplify this even further. by making Q the subject again, so that it is written in terms of the position vectors of the other points, the other vertices, or the vertices, sorry, of the triangle. So this is going to be alpha for A part, that's going to be alpha over 2 multiplying A. And then for the B part, we're going to move this minus B to this side. That will become plus B. So that is essentially going to give us plus 1 minus alpha, because this is going to be minus alpha B. Okay, so maybe we should write that out first. So this is going to be alpha over 2 multiplying C, then minus alpha B. Then we move this minus B to the other side, that becomes plus B. Then we can now simplify for that. This gives us Q equals alpha over 2. So this is alpha over 2a. So I just want to arrange it in the order a, b, c, just like we had it here, so that we can easily compare the two of them now. And for b, we know when we factor out b here, this will be 1 minus alpha, or minus alpha plus 1, anyhow you see it. So this is going to be plus 1 minus alpha into b. Then the last part for C, we have plus alpha over 2C. Okay, so that will be our equation Roman figure 5. Yes. So the last one was Roman figure 4. Yes. So looking at these two beautiful results now, what can you deduce about the point Q here? So you see that this is Q written in terms of the position vectors of A, B, and C. This is Q written in terms of position vectors of A, B, and C. So if indeed there is such point Q, then these two relations should be equivalent. Okay, so that means the coefficient of A here should be equal to the coefficient of A here. The coefficient of B here should be equal to the coefficient of B here, and the coefficient of C right here should be equal to the coefficient of C right here as well. So if that is the case, let's have another page and deal with that. So from equation 4 and 5, from equations, I'll say equating like terms or like coefficients in equations 4 and 5, we obtain. So if we equate like coefficients now, what do we get? We will have, for the coefficients of A, so let's pick the coefficients one after the other. So for the coefficients of vector A, we'll have, so let's draw this more appropriately. For the coefficient of vector A, we will have lambda over 2 to be equal to alpha over 2. So we'll have lambda over 2 to be equal to alpha over 2, implying that lambda equals alpha. So we'll come back to that. Let's say that is A. Then considering the vector B or its coefficients now, that will give us 1, what's now alpha, lambda over 2 should be equal to 1 minus lambda. Okay, so we see that 1 minus alpha, sorry, lambda over 2 should be equal to lambda over 2 should be equal to 1 minus alpha, right? So can we simplify this even further? Yes, since we know that alpha is equal to lambda from equation 1, we can simplify this further, but let's write it out first as it is. So this is going to give us um, that's going to give us lambda over 2 plus alpha to be equal to 1. Okay, so let's keep that first as equation B. And then for the third part, for the coefficient of C, we will have 1 minus lambda to be equal to alpha over 2. So this is going to give us 1 minus lambda equals alpha over 2. So from here, we will have another relation, alpha over 2 plus lambda to be equal to 1. And that will be the third equation. So is there a solution that is consistent that solves, I mean, that actually satisfies all of these equations altogether? Yes, it is obvious that lambda should be equal to alpha. Okay, so we're clear about that. Then if lambda is equal to alpha, then we can solve this and then check that it also satisfies this third equation. So if lambda is equal to alpha, then substituting equation A into equation B, what do we get? We will have alpha, or say that is going to be alpha over 2 plus alpha to be equal to 1. So what will this give us now? This is going to be, when we take the LCM of that, that is 2. So this is going to be alpha plus 2 alpha equals 1. And from here, we get 3 alpha over 2. So this is 3 alpha over 2 equals 1. And this gives us alpha equals 2 over 3. All right. So that is our alpha. And then we know that that is also going to be equal to um, lambda. And can we confirm that here? If we put that here, if we put alpha equals 2 over 3 here, so this is going to give us 1 over 3 plus 2 over 3, and that is going to give us our results as 1. Okay, so we have seen that alpha is equal to 2 over 3. So then what can we say then? If we substitute alpha to either equation 4 or equation 5 now, then we will have a relation that we need between the vector q, okay, of that point of intersection of the two medians, and the vectors A, B, C, which are the position vectors of the vertices of the triangle. All right, so let's go ahead and do that now, substituting all of this into equation 5. Then substituting this into equation 5, we'll have Q to be equal to, so we know alpha to be 2 over 3, so we'll put that here. So we're going to have this to be 2 over 3. Alpha is 2 over 3, then divided by 2 multiplied by A. Then plus 1 minus alpha, so this is going to be plus 1 minus 2 over 3, okay, multiplying vector B. Then the third one, that is alpha over 2, that is still 2 over 3 divided by 2, so that's going to be plus 2 over 3 divided by 2 multiplying C. So at the end of the day, what do we have this to be? This is going to give us Q equals, this 2 we cancel this 2, we have 1 over 3 here, so this is 1 over 3 into A. Then 1 minus 2 over 3, that is 1 over 3, you can check that. This is also going to be 1 over 3B. And then 2 over 3, again, this 2, we cancel this 2, we have 1 over 3C, so this is 1 over 3C. So we now have a relation between Q and all the points, I mean the position vectors of the points of the vertices. So this is going to give us Q equals 1 over 3 into A plus B, okay, plus C. All right. Does that make sense? Yes, it makes sense. We'll talk about how it makes sense shortly, but does it conclude our analysis? No, there is something we are driving at. We are not at our destination yet, but this is a good and interesting intermediate result. So please pay attention to this now. You should observe that now we have an extension to what we discussed or discovered, so to speak, in the last chapter. In the last chapter, we discovered the fact that because this is the midpoint of A and C, for instance, then its coordinates will be half of the sum of the coordinates of A and the coordinates of C, okay, which is perfect. Now imagine if you have 3 points and then you want to pick the middle of those 3 points. What do you think that should be? That means you should add up the coordinates of those 3 points. So if you add up the coordinates of 3 points, that means you have added up three things. And then if you're going to take the average of that or the middle of that, then you should divide it by 3. And hello, that is exactly what we just got now. Q happens to be the middle of the triangle, okay? And it is also called the centroid of the triangle, or the center of the area of this triangle. So this tells us the position vector of one end, this tells us the position vector of some other end, and this some other end, or all are vertices of the triangle. So if you want to pick the midpoint of the triangle, it has to be the average of these three. So it's this all of these coordinates added up, then divided by 3 will give us the coordinates of that midpoint. Okay, so this is an interesting intermediate result that you should have in mind as well. So even if you don't need to do all of this analysis at some point, you might need to know this result because it might help you to simplify some other problems you may come across. Okay, um so now let's move on. Just like, I mean, this is similar to what we had here. Here we said that E was equal to half of A plus C. I mean, that is just like we're taking average of A and C because it is the center or the middle of the points, okay, the connection between the points A and C. E is the middle of it, so E should be half of this plus this. So Q is now the midpoint of ABC, so it should be 1 over 3 of A plus B plus C. So that's what we have just established now. So please have this result in mind, know what its implications are, know how we came about it, that is fine. Even if you can't remember how we came about it, you should know the implications of this. This is simply telling us this is the midpoint of the triangle, okay? But like I said, this is not our destination yet. We are not at our destination yet, okay? So what do we really want to show? Don't forget, we want to show that the midpoint or the median through the point D, the median through the point D is AD. So we want to show that AD also passes through the point Q. I mean, once we're able to show that AD also passes through the point Q, then we have established that the medians are concurrent. That means the medians meet at the same point. So wherever these two medians have met must be the same point that the third one will pass through. So if we will prove that the third one passes through this point, what do you think we should drive at? Again, like I said, if you want to establish a proof, you should have your destination in mind. So what is our destination, or what should our destination look like? We want to prove that this line AD passes through the point Q. If that is the case, then just like we did for BE and CF, the vector AQ must be shown to be concurrent, sorry, to be collinear with the vector AD. So that means we should seek to establish that, concurrency means that we should now seek to establish that the vector AQ is a multiple, say beta, of vector AD, is a multiple of vector AD. So that means we should be looking at establishing a relation between the points A, Q, A, D. So that is the points A, Q, and D. Now let us see what that relation is. Once we have that relation, then we see if we can, from that relation, establish that AQ is a multiple of AD, or AD is a multiple of AQ, if you like. Okay, so we don't know what beta is, but I guess our analysis now will show exactly what beta should be because we have found those multiples already for the other medians. Okay, so it may just apply to the third one as well. So we see that shortly. Now let us move on with that. So don't forget our destination. We need to establish a relation now between A, Q, and D. D is not part of the vertices. We have only established a relationship between Q and the vertices A, B, C. So to proceed now to establish a relationship between Q, A, and D, then we should find a way to bring D to the result we have just obtained now. And how do we do that? it's quite easy because we have written out all the relations already. So looking at the relations we wrote out for the point D, we know that D is equal to half of B plus C. So where we have B plus C, we can replace it with 2D. So once we have that, then we have an equation that relates Q, A, and D, which is what we really need to actually conclude on our proof here. Okay, so now let us go ahead and do that. So we have this relation. This is an interesting result. Although it is not our destination, it is an interesting result. So I am giving it emphasis here so that we can easily notice it is one of those interesting geometric results when it comes to the discussion of triangle. And in fact, when it comes to the discussion on centroids, as we will do in the course of this course, okay, so to speak. Okay, now look at this now. We want to establish a relation between Q, A, and D. That's our business here. So we have Q related to A, B, C. So we want to get rid of this and just see how we can bring D into the whole process. Okay. So we now say that using equation, what is this now? That equation that we had for D. Using equation 2, Roman figure 2 now, we know that D is equal to half B plus C. Okay, so we now say that. So let us keep this result for now. Let us say this is equation 6, or say equation star. All right. Then again to proceed, before we finalize, we say that from equation 2, our coordinate of point D or position vector of D is 1 over 2 into A plus C. Is that A plus C or B plus C? Please let us check again to be sure. It was B plus C, please. 1 over 2 into B plus C. So this is 1 over 2 into B plus C. Let us correct that. B plus C. So this implies then, of course, if we multiply both sides by 2, this means 2 multiplying the vector D will be equal to B plus C. And now we can insert this in this relation. So let's say this is equation 6. We can put this right here. So therefore, using equation star now, we can say that Q will be equal to 1 over 3 into A plus, so instead of B plus C now, we can write, this is B plus C normally. Okay, this is B plus C. Okay, let me use brackets still. We can now write it as 1 over 3 into A plus, instead of B plus C, we are putting into D. All right, so this gives us a relation between Q, A, and D as we want it. So can we now play around with this and see if we can indeed establish from here that AQ is a multiple of AD. So let's go ahead and do that now, and then we end the analysis there. So to proceed, we can get rid of these 3, just multiplying both sides by 3. We're going to have this to be 3Q equals A, okay, plus 2D. So that is it for now. What exactly do we need? We need to show that this, or we are driving at a relation between this and this. So if we will do that using position vectors, then we know AQ would be Q minus A, and then this will be beta, where beta is going to be some number, then into D minus A. So AD is D minus A. So we are interested in having Q minus A and D minus A. So we want to bring Q and A together, and then also bring D and A together. So we need that to proceed. So if we will have Q minus A, pay attention now. You can see that Q is being multiplied by 3. So if we're going to have Q and minus A together, then we should have 3Q. So just pay attention to this, minus 3A. Why are we doing that? So that we can have Q minus A. Since this is already multiplied by 3, let's add minus 3a to it, so that when we factor out 3, we'll have q minus a. But what have we done here? We have added minus 3a to this side, so we should add it to the other side as well. So this will be equal to a plus 2d, then minus 3a as well. So we have to add minus 3a to both sides for consistency of our equation. So this becomes 3 into q minus a is equal to a minus 3a. So we can do that arithmetics like that. We know this will be 2d minus 2a, because a minus 3a will become minus 2a. So from here, we can see that 3 into q minus a is equal to 2 into d minus a. So life becomes very, very, very easy now. Have we got to our destination yet? Don't forget, we need q minus a to be some multiple of d minus a. So have we got there? Yes, yes, yes. So we can just divide both sides by 3 again. So this is going to give us q minus a to be equal to 2 over 3 of d minus a. Okay, so this is 2 over 3 of d minus a. All right, so what is q minus a? Q minus a is aq. So aq is equal to 2 over 3 of d minus a, which is ad. So with this, we are good to go. We can let go of this bracket now. So this is just 2 over 3 ad. So what does this tell us? This tells us that indeed AQ and AD are collinear. So this means that AQ and AD are collinear. That means that this line from here to here indeed passes through these points. Okay, so let me restore that. I want to write this with a different color. Yep. So this indeed passes through the points Q. So that's the implication of the results we have just obtained now. Because we have established that this AQ is collinear, that means along the same line as AD. So that means indeed the third median passes through the same point where the other two actually intersect. And therefore, the three medians of a triangle are concurrent. Full stop. So we're done. We have now established that indeed the three medians of a triangle are concurrent. So that took a lot of journey or a lot of analysis, but this example is rich in a number of ways, in the sense that it tells us a number of things about the medians and their point of intersection. So we will take note of them shortly. Yes, we're done with our analysis. I would just want to write out the conclusion from here. Then we will observe some interesting results that we have now obtained concerning the geometry of a triangle by just playing around with vectors and position vectors. So you see how interesting this could be. All right, now, so we have this implies that, sorry, I didn't intend to use that here. So this implies that, say, thus AQ and AD are collinear. Hence, AD, or say median AD, also passes through the point, Q of intersection, don't forget, of B. What with the other two medians? Also passes through the points of intersection of the other medians B, E, and C, F. Okay, through the point Q of intersection of medians B, E, and CF. So we now say that therefore the medians of a triangle are concurrent, meaning that they pass through the same point. So the median of this arbitrary triangle that we have chosen, actually all the medians of this triangle pass through the point Q. So what other interesting thing have we observed here? We have seen that AQ is 2 over 3 AD, and if we did something similar for the others, we'll also see that. So looking at this now, we can see here that we found our alpha the other time to be equal to 2 over 3, which means lambda is also equal to 2 over 3 because they are equal. So we have also seen that this relation for this third one is also 2 over 3. So that tells us that AQ is 2 over 3 AD, and similarly, how we came about alpha. Alpha was this relation, so that means BQ is also 2 over 3 BE. So BQ is 2 over 3 BE, and we have also observed that CQ is 2 over 3 CF. So those are the results we have obtained in this lesson. So we have seen that AQ, this length from here to here, is 2 over 3 of the total length. And that means this length from here to here is 1 over 3 of the total length of this median. And similarly, the length from B to Q is also 2 over 3 of the length of the total length from B to A. And just as this one, the length from C to Q is 2 over 3 of the total length from C to F. Okay, so that's an interesting result. It means that the distance from this midpoint to the centroid is 1/3 of the distance from that midpoint to the opposite vertex. Okay, so that's another interesting result. So a lot of things can be deduced from this analysis, considering about or concerning the geometry of a triangle. All right, but that is that. So with this analysis, we have been able to establish, as required, that indeed the medians of a triangle are concurrent. They pass through the same point Q. And now you know how to deal with situations where we need to prove that some lines or some vectors are concurrent. You just need to prove collinearity. Okay, so that is that about that. Thank you for watching. That is the end of this chapter. We'll see in another chapter as we take analysis of vectors some steps further. Thank you.